Hello everyone, this is 𝐒𝐴𝐬𝐻𝐚𝐿. I'm going to present our work titled OptiGame, Game-Theoretic Enhancement for Optimistic Rollups through Bayesian Strategies. The authors are myself, MGM Mehdi Hassan and Mohammad Ashikur Rahman. The first and third author are from Florida International University. The second author is from Iona University. To give a brief overview of the presentation, first I will be going through the introductory information. Then I will be talking about the contributions that we made through this work. Then I will be discussing the game design, the current traditional implementation, and what we are proposing in terms of the game design. Then we'll be talking about the technical details section, which will discuss the way we define the belief function and also the utilities. Um, Followed by the evaluation section, where we will do experimental evaluation for uh, validating the effectiveness of the proposed game design, and I will conclude the presentation through the discussion section. To begin the introduction section, I will be providing some background information that will help motivating the work. So, blockchain secured the monetary transactions. However, scalability problem hinders its utilization. Like you can see, Visa, the daily debit or credit card that we use, have a transaction per second of 4,000 and it can go up to 65,000. But for one of the most like widely used cryptocurrency as Bitcoin, that has only transaction per second of 7. It is not scalable at all. So there's two ways to scale. One is the scaling the base layer. It's called the layer 1, and the second one is outsource the work to a new layer called the layer 2. So to provide a comparative analysis of the two methods, the layer 1 is the modification of the base layer protocol of the blockchain network, while the layer 2 is to involve the use of off-chain services on network to improve the scalability. The approach that is used in layer 1 is larger block size or new consensus mechanism. In terms of layer 2, it's like sharing the transaction ordering and processing workload with the off-chain. In terms of fees, a layer 1 varies, it can be high, but layer 2 is generally lower than the layer 1 solutions. The transaction rate is better for layer 1 than the without any scalability. However, layer 2 is faster. The prime examples for layer 1s are like sharding, DAG, alternative consensus, while the layer 2 uh, prime examples would be payment channel networks, optimistic rollup or rollup, plasma, etc. Now let's talk about the optimistic rollup. So optimistic rollup system or ORS is one of the prominent L2 scalability solutions. They reduce the on-chain operation and minimize the transaction fees. The widely used optimistic rollup system are Arbitrum and Optimism. However, they suffer from centralization concern due to the sequencer, a single entity that is responsible for ordering the transactions. The introduction of multiple processors, which are called the aggregators, in the L2 rollup ecosystem addresses this centralization concern. Now let's see how a transaction takes place in optimistic rollup system. So L2 tokens are required for the OS transaction, and there is a smart contract that resides in L1 that is used for exchanging the L1 coins with the L2 tokens. So user have two options. They can either send transaction to the mempool directly, uh, like by exchanging the layer 1 coins first from the smart contract and then send it. The second one would be via the L1 smart contract, where the user will send the coins to the smart contract and that will be sent to the Bedrock's mempool as a layer 2 transaction. The aggregator collect the transaction from the mempool. They execute the transaction, generate the cryptographic aggregate along with the Merkle root of the L2 chain, and submit them to the verifiers. The verifiers on L1 monitor the submissions. They can raise challenge if they detect any invalid or fraudulent transactions. If fraud is proven, then transactions are reverted and the fraudster loses the bonded deposit. If not a valid if it's not a valid challenge, then transactions are added to the main chain. However, since there is a mistake from the verifier, he will be fined. Now let's talk about the motivations behind this work. So there is a verifier's dilemma. Challenging a batch can get honest verifier slashed, like by the mistake. So rational actors often stay silent, opening the door to undetected fraud. Aggregators' advantage is there. Like incidents or arbitrum and optimism show dishonest aggregators manipulating state truth for illicit gain when they expect no challenge. There are the throughput choke points. So each dispute freezes settlement for hours, erasing much of the roll-up's scalability benefits. And there is the inadequate incentive design. So the current protocol rely on static penalties. They lack positive rewards or reputation mechanism that cultivate long-term honesty. And finally, the research gap. Prior game theoretic models are mostly static and ignore the uncertainty, leaving the security scalability tension unresolved. From getting motivated through the issues that discussed in the last slide, we made the following contributions through this work. We rigorously model aggregator versus verifier interactions, proving that optimistic rollups naturally instantiate an inspection game and quantify how throughput loss, verifier slashing, and adversarial gain shape a strategy. The proposed OptiGame augments the classic model with dynamic Bayesian beliefs about aggregator and a repetition mechanism that raises reward for good behavior and penalties for bad, realigning the incentive towards honest batching. We introduce a solver that derives a mutable payoff matrix from system parameters and live player actions, ensuring the Bayesian Nash equilibrium remains security preserving even as conditions change. Finally, a smart contract prototype on Optimism Sepolia testnet demonstrated that higher throughput sharply reduced verifier slashing and near eliminated the fraudulent batches versus the conventional protocol. So now we'll talk about the game designs. First, we'll talk about the conventional inspection game. You can see the expanded form of the game here. So there are two players. First is the aggregator, which is shown by the A circles and the verifiers. And you can see the verifier has the same information set. That's why the dotted line here. So verifier doesn't know which action the aggregator took. It could be the honest or the other, but he doesn't know. So his action doesn't depend on the action of the aggregator. So aggregator can take two kind of actions. The first action is H, that means aggregator's move when it is sending the valid Merkle state truth proof. The other one is D, that means aggregator's move when it sends manipulated Merkle state truth proof. On the other hand, the verifier can take one action, that is C, verifier's move when it challenges a proof, and I, the move when the verifier ignores challenging the proof. So these are the outcomes with each type of action set taken by each of the players. And this is the conventional form of the game. Now let's talk about the proposed Bayesian game that we are proposing in this work. So as you can see, this is the expanded form of the game, and there is a belief function. So let's go through each of them. So theta is the probability of aggregator being malicious. So 1 minus theta is the other probability of being honest or regular. And this for a malicious actor, they can take two type of actions. One is like the normal, and another suspicious. And by suspicious we mean they will do an adversarial action basically. So the probability is shown by this symbol, and then for the regular aggregator, they can also take normal and suspicious action, but for their suspicious action we will just assume that this is something they did unintentionally or mistakenly, and the probability is shown by this symbol. And then the verifier, they can challenge, and the probability of a verifier challenging a valid proof is pi, and the probability of verifier challenging an invalid proof, that is actually the challenge that's supposed to happen, that is shown by this omega. So other than that, alpha means each payoff for the aggregator, and nu means each payoff for the verifier. Now we'll be talking about the framework and how that will work to incorporate the game into the existing system. So there is a modular triad. So the first one is symbolic mathematics solver that computes the initial payoff matrix from system rewards, cost, and target security probabilities. Then there is the Bayesian game engine that runs the live aggregator verifier game using belief parameters that were discussed in the last slide. And finally, there is a repetition mechanism that updates each aggregator's score shown by beta and the verifier's belief after each batch. So adaptive incentives are there, the dynamic part of it. So real-time actions are fed into the solver when the behavior diverges from the expectation. Low weight tweaks to the payoff matrix realign the Bayesian Nash equivalent towards the honesty. Now we will start the evaluation part of the presentation. So at the beginning we show the expected utility gains by batch values. So expected utilities versus the batch value, and by that we mean different valued batches. So average utility for aggregators and verifiers across 3 batch value ranges are shown here. Under the legacy inspection game, verifier utility stays flat, as you can see for all the cases, while aggregator gains only fraud goes undetected. The Bayesian OptiGame that we are proposing curve lifts honest aggregator utility by 40% around and stabilizes verifier returns, making honesty the dominant strategy. So that is one of the evolution that validates the effectiveness of our work. The second evaluation that we performed is the throughput stability across aggregator verifier splits. So we do different portion of aggregator and verifier matches in terms of the proportion, and then see how much it affects the throughput. So transaction per time at 5 aggregator versus verifier ratios that starts from 3 to 1 and ends at 1 to 1 as the batch size grows, as you can see shown in the x-axis. So OptiGame lifts throughput for every mix and shrinks the gap between aggregator heavy and verifier heavy setups. So it reduces the need for having more verifier because that gap is shrinked. The balanced 1:1 reaches throughput once possible only at 3:1 for the baseline. So that is an improvement that we do through our proposed Bayesian game. The next evaluation is the slashing of the verifier that we show through the heat maps. So we do 2 cases like the conventional and proposed, like we did in the last 2 slides as well. So the average collateral slashed per verifier across the aggregator verifier ratios and 3 threshold value bands. The inspection game shows up to 3 times higher wrongful slashing in aggregator heavy regimes. OptiGame's reputation for filtering cards slashing uniformly, that means that has a steep drop of 55% in the 5:2 scenario. Now moving on to the next evaluation, which is the integrity loss containment under the OptiGame. Again, we have both the inspection game case and the Bayesian game case, and we do this transaction integrity loss evaluation. So the integrity hampering percentage, that is the fraudulent value of percentage, versus the aggregator honest probability, that is from 10% to 90% at 3 aggregator versus verifier mixes. The baseline integrity loss climbs to 60% when honesty less than 20% and verifiers are outnumbered. OptiGame keeps loss between 10% even if there is in a 3:1 mix, thanks to the reputation driven deterrence. So in our final evaluation, we do the aggregator behavior over time. So how aggregator behavior dynamics changes, and we count the good, gray, and bad aggregators over 100 batches while varying the invalid batch challenge probability from 0.7 to 0.9. Also, the chance of bad aggregator submitting a valid proof, that we change from 0.15 to 0.35. So raising that first probability to 0.9 nearly eliminates the bad actors to 80% and expand the good set. Turning the second percentage shows the OptiGame nudges gray aggregators towards good behavior without swelling the bad pool. Finally, in conclusion, by coupling a Bayesian game model with on-chain reputation, Our proposed protocol turns honest batching into the dominant strategy, cutting fraud and dispute overhead while preserving L2 throughput. Fewer fraudulent proofs mean verifier can slightly less reward, yet they also face far fewer wrongful slashings. The net effect is more robust and trustworthy rollup. A symbolic solver continuously retunes penalties and rewards, giving OptiGame a flexible foundation that can evolve with changing network conditions or policy goals. In our future work, we'll investigate whether the reputation layer can reduce proof costs or verify latency when zero-knowledge proofs replace fraud proofs. Finally, I want to thank you all for listening to my presentation, and if there is any question, I'll be happy to answer.